Hi everyone, I am Hardik from Cornell University. In this video, I am going to talk about composing Dataplane programs with µP4. This work is done in collaboration with Mariana, Nokia Bell Labs, Praveen Anand, and Ned at Cornell University. Over the past decade, networks have seen great transformation due to emergence of software-defined networking, Dataplane programming languages like P4, and domain-specific hardware. Now, networks increasingly look like any other software system, for example, operating system or database. These large and complex software systems are built in an incremental way, using modular approach for programming. That is not the case with network data plane software. To build data plane software, we still write code at very low level. We still lack the ability to develop network data plane programs in a modular way. And this is a shame because according to MIT professor Barbara Liskov, modularity based on abstraction is the way things are done. So why modularity is so important? Well, to manage scale and complexity of large software system, it is better to decompose them into small pieces and independent features so that we can design, develop, and test them in an efficient and independent way. Then we can develop libraries of these common features. We would like to be able to reuse packet processing code from libraries rather than having to rewrite them from scratch in each application. Then we can develop this library using high-level abstraction or code, and we would like to let compiler port these libraries to different target devices by taking care of low-level details. So next we look at how current data plane softwares are built. And for that, I'm going to take an example of widely used and well-known and open source data plane program, Switch. It is developed using P4 language, and the software is maintained and developed by P4 community. So it implements a variety of features. It implements 15 to 17 different features and tens of protocols. And currently we are going to have a look at only a couple of routing protocols. As you can see, IPv6 related code fragments are guarded using IPv6 preprocessor, and similarly IPv4 or any other routing protocol. So we are actually writing data plane programs with a spaghetti code, which is really hard to extend, reuse, or maintain. So the next question we ask, what are the challenges in developing this kind of independent features in a modular way? And we are going to look at three particular challenges posed by P4 programming language. First, P4 programs are monolithic. As we have just seen, code fragments for independent features are entangled throughout the code base. Second, P4 provides multiple sublanguages and different mechanisms to express packet processing. For example, it provides programmable parser using state machine-based sublanguage, then match and action control block to modify headers, parsed headers, and to interact with a fixed function exposed by target devices, it provides something called extern. And programmable parser and control blocks are incompatible features. For example, if feature 1 wants to transfer program control from its match and action control block to parser of feature 2, it is not possible because these two follow different abstract machines. In addition, P4 programs are tightly coupled with architecture. Device vendor provides certain programmable interfaces as a part of architecture, and P4 programmers have to implement these interfaces. For different target architecture, these interfaces change. So P4 program written for one architecture cannot be reused on another. To address these challenges and allow programmers to develop data plane program in a modular way, we propose µP4. µP4 is based on a simple functional model that distills packet processing down to its essence. If you are familiar with click modular router, µP4 follows similar ideas. Operationally, µP4 has a 3 stages. One, µP4 module reads packet from logical input buffer. It processes using 3 canonical stages, parser, controller, and deparser, and then it writes back to our logical output buffer. These read and write buffers are actually just logical buffers. Here the idea is programmers doesn't have to worry about or understand the details of low architectures, how packet processing is implemented on a given architecture. Rather, they should just focus on expressing packet processing logic for their applications. Next, we look at how µP4 provides composition, allows programmers to express composition. And for that, we are going to take example of a firewall, µP4 module, and routing. And if you want to compose these two µP4 module in a sequential manner, then all we have to do is to attach output buffer of firewall with input buffer of routing. And this composed entity can again be called as a µP4 module by if we associating input and output buffers. Next we look at how µP4 allows a logical program to translate down to the on a given architecture. And for that, we develop a compiler. It takes program written against logical pipeline as input, and it translates program for a given architecture in P4. For example, it can translate to portable switch architecture and generate P4 source code for it. It has a two key passes, mid-end. In mid-end, it transforms every match and action control every deparser into match and action control block, and in backend, it translates this homogenized IR to target specific data plane architecture. So here, next we are going to look at µP4 in action. So here idea is we want to develop a modular router using IPv4 and IPv6 protocol. Here is the scenario, and programmer implements parser, control, and deparser. Here we are going to look at how next hop is used to forward packet processing. Currently in this example, we haven't attached any IPv4 or IPv6 routing module. So all the packets will be dropped. And now we attach or we compose routing protocols together. So programmers have to implement unicast interface, do some longest prefix match, and return next hop as a part of longest prefix match. So here IPv4 module returns next hop. Similarly, IPv6 module returns next hop as a part of its packet processing. And our router main function can use this next hop and modify Ethernet headers. And then all it has to do is invoke IPv4 and IPv6 module. And µP4 allows to compile libraries and reuse them, as you can see here. And now because we have composed router with two routing protocols, we will be able to have a reachability using IPv4 as well as IPv6. So we can see the pings for IPv4 and IPv6. Finally, we evaluated µP4 on 3 parameters: expressiveness, portability, and efficiency. For expressiveness, we develop a set of library functions. For portability, we develop a 2 backend, one for software switch BMV2 and another for hardware target Tofino. And to evaluate efficiency, we compare resource utilization against handwritten monolithic Tofino programs. So in this slide, I'm showing you here a set of µP4 modules here. Then P1 to P7 are different programs or profiles that are created by composing different µP4 modules. And for every profile, we created a Tofino specific P4 program. We evaluated resource utilization using number of match and action consumed by programs. As you can see, µP4 compose program consumes a lot more match and action stages compared to its monolithic counterpart. More analysis is given in the paper. What µP4 is our ongoing work, and we plan to optimize µP4 for resource utilization. And we already have a design for packet application and multicast, but µP4 compiler doesn't support it right now. And we are planning to enable a set of features. Finally, takeaways. Liskov was right. Modularity based on abstraction is how things are done. As a part of that, we develop a high-level abstraction for data plane programming. We wrote a compiler for that, and we gain a first-hand experience in developing a modular router. Code and examples are written on a kernel NATLAB µP4. Thank you.
Thank you a lot for the great talk, Hardik. So now we will take some questions from Slack and the QA window. So the first question is, will it be possible to use µP4 to create something like switch.p4, considering such high overhead on resource utilization?
Yeah, the current resource overhead is due to our implementation of prototype, and we don't believe these overheads are fundamental in most cases. The source of the overheads are because we are emulating parser deparser into match and action control blocks, and that is the source. But we have a compiler, or we believe there are compiler optimization that can eliminate this overhead. Yeah.
Okay, great. So the next question is from Haki Aaron on Slack. So the question is, could one use µP4 to support multi-tenancy or virtualization of a programmable switch, such as compiling together macro pipelines of different tenants?
Yeah, I think it could be used, but what we do not do right now is to partition the resources on the host to different tenants. That's what we don't do. I mean, we compose the program together, but we don't interfere with resource allocation of target architecture.
Great. Yeah. So if you are aware, the next talk, Lyra also proposes a language and a compiler for data plane programming. So I want to hear what's your opinion and how do you compare µP4 with Lyra, because they are kind of like solving very similar problems on portability, expressiveness, and yeah. And I want to know, like, well, how do you compare these two languages?
Yeah. So I think it's very interesting work. It's a great work. One of the key fundamental difference between Lyra and µP4 is that Lyra provides a one big switch abstraction for the entire network. And what µP4 focuses on a single device and allows to combine small packet processing cores and build a data plane for one device. Lyra is about expressing or providing programming the entire network as one single pipeline, and that's the main difference between these two.
Okay, great. Okay, so so the next question is from Anira, and the question is, can you compare µP4's approach to P4's PSA, portable switch architecture? Yeah, what's the difference and how do you compare them?
Yeah, so PSA is benchmarks the hardware that say every hardware should implement this architecture, where µP4 doesn't put such a restriction. It's the compiler that takes down and puts to different target devices. So in that sense, they are fundamentally different, saying that PSA enforces you to write a program in a particular way, and where µP4 allows you to write a program in a logical way and then takes care of lower level details on different target devices.
Okay, thank you very much.
So thank you, Hardik, for the talk. And while Q&A questions are filtering in, I guess maybe I can ask a couple here. So first, I guess could you go into a little bit more detail about the overheads of µP4 and whether or not you think they're fundamental, what you might do with them?
Yeah. So the current overhead that we have shown in the paper is due to implementation of prototype. We don't think it's a fundamental overhead. We believe there are optimization in compiler passes that can be done to eliminate this overhead. And this overhead are the converting parser deparser or emulating them into match and action control blocks. That's the source of the overhead. And we believe with optimization, we can eliminate them.
I see. So another question here. So could you use µP4, for instance, to support multi-tenancy if different programmers were to sort of write separate pipelines that you would then merge together using your tools?
Yeah, so here the multi-tenancy is a pretty much broad term. what do we want to do? Do we want to provide some sort of a slice of resources? If it is the case, then we don't, per pipeline, we don't provide isolation in resources. In µP4, it just composes them. So if you just want to run multiple programs together in some fashion, then yes, multi-tenancy is possible, but with resource allocation and isolation, no.
Great. And I think one more question that I'm curious about. So we touched on this a little bit during the morning session, but how would you compare and contrast your work versus the other ones? Especially, I don't think you talked about the switch code generation work, right? Like, would your work be complementary to that, or is there something interesting there?
The switch code generation. So the switch code generation really focuses on generating a different or maybe equivalent program to allocate on hardware. µP4 doesn't really interfere with resource allocation on hardware. It's a source-to-source compiler. So ultimate compilation of the resource allocation on hardware is done by the target-specific compiler. So it's kind of a complementary VC.
I see. Great. Yeah, so why don't we switch back to the first talk then. Thank you, Hardik, again, for answering all those questions. So actually, there's one that just came up that maybe we have time for. So Minlon is actually asking, how general is µP4's portability to different target architectures?
So we have a backend for two target architectures. One is for software switch V1 model, and another is for Tofino TNM. How general is, we can only say with these two architecture, we do not have a huge set of architecture to say it's really general, but we try to capture the basic idea of packet processing and create an abstraction for entire data plane, not only for parsing or match and action table like this. So we hope it's general, and over the time, as we deploy on different architectures, it should be quite visible.